Okay, so today we are going to talk about the assignment problem, assignment model. So the assignment model is like the transportation model, is the prototype example of the linear programming. So if you look at any operations research textbook, then you're going to see these two examples all the time: the transportation and assignment problems. So I'd say the assignment problem is like the transportation problem, and they are both the fundamental combinatorial optimization problem in the branch of the operations research in mathematics. And the goal of the assignment problem is to assign a number of resources. So the resources usually the workers or the machines. So we assign the number of resources to an equal number of activities or tasks. So usually that can be the jobs, okay, that can be carried on. And while at the same time minimizing the total cost of allocation, okay? So the finding the best person or the best machine for a specific job would be an apt description of the assignment problem. And here the best means the least cost way of assignment, okay? So the problem of assignment arises because the available resources, such as man, machines, etc., have the varying degrees of efficiencies, for performing different activities, right? So the cost or profits or loss of performing the different activities might be different. So the assignment problem is definitely a highly useful tool for the operations and the project managers for optimizing the cost, right? So in general, the assignment problem can be described as shown in this screen. So we consider a certain number of resources. So like I said earlier, this could be the machines or the people, workers, and the same number of activities or the jobs to be conducted, right? And as a general rule, and the objective is to minimize the total cost of assigning every resource to an activity. So as a general rule, all the jobs must be performed by exactly one machine or one worker. And every machine or every worker must be assigned exclusively to one job, okay? So in this cost matrix, the total number of rows is equal to the total number of columns, okay? And the element here C sub ij represents the cost of assigning worker or machines to the job in a job shell example, okay, for example. And so the assignment problem is basically the special case of the transportation problem that we discussed last time, where the machines represents the sources and the jobs represents the destinations, right? And of course, the supply amount at each source exactly equals 1 in the assignment problem. Likewise, the demand amount at each destination also exactly equals 1 in the case of the assignment problem. So actually, the assignment problem can be solved directly as a regular transportation problem. However, the fact that all of the supply and demand amount equals 1 has led to the development of a simple solution algorithm, which is called the Hungarian algorithm. Okay, so later today we will talk about the Hungarian algorithm. But first, let's look at the mathematical model for the assignment problem. Okay, first we define decision variable x of ij equals 1 if the resource number I is assigned to activity J and 0 otherwise. Okay. Then we can construct the assignment model like this. Again, the objective is to minimizing the total cost of assigning every resource to the activities. And we do have two different sets of constraints. So first set of constraints is that each resource is assigned to exactly one activity. And second set of constraints ensures that each activity is assigned exactly one resource. Okay. So as you can see here, this is a special case of transportation problem with here supply amount and demand amount, each equal to 1. Okay. Any questions so far? Okay.
No questions for me.
I'm sorry, what did you
I have
say?
no questions. I haven't got any question.
Okay. So let's move on to the next screen. So the assignment problem has the important properties. The first one is that for each row, exactly one assignment is made because each resource is assigned to exactly one activity, right? Likewise, for each column, exactly one assignment is made because each activity is assigned exactly one resource, right? So therefore, if a number delta is added to or subtracted from every cost in a certain row or column of the cost matrix C, then every feasible set of assignment will have this cost increased or decreased by the same number delta. And the optimal set of assignments remains optimal. Okay? So for example, like it says here, if you add delta to row number 1, the first row, then the total cost is definitely increased by just delta. Okay. And this increment is independent of the value of x. Is the second property. Assignment problem has another property that if all of the assignment costs are non-negative, then and if there is a set of assignment with total cost equal to 0, then that set of assignments must be optimal. Okay. So like I make a comment here, the Hungarian method that we are going to talk about in a minute solves the assignment problem by adding and or subtracting certain amount of quantities in each row and all columns until an assignment with 0 cost is found. Okay. So I would say that finding the 0 cost assignment is the goal of the Hungarian algorithm. Okay. So let's take an example for the second property, the assignment problem. So we consider, in this case, 4 different machines to process 4 different jobs, okay? And the processing time for each machine and job assignment is shown in this figure, okay? Then our question is, what is the assignment? 1 job per machine, which will minimize the total processing time. So to find the 0 cost assignment, let's first subtract the smallest cost from each row. So here, the smallest cost in the first row is 4. So the amount of 4 is subtracted from the first row. So we will have 4 minus 4 becomes 0. 6 minus 4 becomes 2. 5 minus 4 becomes 1. 5 minus 4 becomes 1. Okay? Likewise, we subtract the smallest amount from the second row. Okay, so the smallest number in the second row is 4 again. So 7 minus 4 becomes 3. 4 minus 4 becomes 0. 5 minus 4 becomes 1. 6 minus 4 becomes 2. Okay. So likewise, you do the same kind of computation. Okay. Subtract the smallest amount for each row and subtract the same amount from every element in each row. So for example, the bottom row, the smallest amount is 3, right? So we're going to subtract 3 from every single component from the row number 4. So 5 minus 3 becomes 2, 3 minus 3 becomes 0, 4 minus 3 becomes 1, 7 minus 3 becomes 4. Okay. So by doing this, at least 1 0 values are introduced into each row, right? So here we have 0, 0, and we have 2 zeros, and we have 1 0. The fourth row, right? So this process is called row reduction. Okay? Now we're going to do the same kind of computation for each column. So we're going to perform the column reduction. Okay. So now from each column we subtract the smallest cost, smallest amount. So here, if a column already have a 0, right? Like the first column, second, and fourth column, then nothing's going to be changed, right? Otherwise, a 0 is introduced in the column. So in this case, the smallest amount for the column number 3 is 1. So we're going to subtract 1 from every single component here. So 1 minus 1 becomes 0. 1 minus 1 becomes 0. 2 minus 1 becomes 1. 1 minus 1 becomes 0. Okay. So as you can see here, only column number 3 lacks 0. So only column number 3 is replaced. All the other columns remains the same. Okay. Now, examining the cost matrix, the new cost matrix, we can find an assignment with total cost equal to 0, right? So if you choose this 4 element and then go back to the original cost matrix down here, the number corresponding to this location is 4, right? And here we have 4 down here, and for this location we have another 4, and for this location we have another 4. So basically, if you add up these four numbers, 4 plus 4 plus 4 plus 4, that will gonna give you the minimum assignment cost of 16. Okay. And of course, this is the optimal assignment. Okay. So as a conclusion, you're gonna say you're gonna assign machine number A to job number 1. So A to 1, and machine B to job number 2, and machine C to job number 4, machine B to job number 3. So that's the optimal assignment and the corresponding optimal assignment cost. Okay. Any questions so far? No questions? Okay, then let's move on to the next case. Sometimes, however, you cannot find the zero-cost assignment after the row reduction and the column reduction. Okay, so in this cost matrix, for example, the machine C cannot be assigned to both jobs number 1 and number 4 at the same time. So in this case, one job must be assigned a machine with positive assignment cost. Okay. So now I'm going to talk about the Hungarian algorithm, which can solve this kind of issues. Okay. So this screen summarizes the detailed steps of the Hungarian algorithm. So like it says here, the Hungarian method solves the assignment problem by adding and or subtracting the certain amount of quantities in each rows and or columns until you find the zero-cost assignment. Okay. So if the number of the rows and the columns in the cost matrix unequal, then before you start this the Hungarian algorithm, the assignment problem has to be standardized. Okay. So in this case, the Hungarian method. So in this case, the Hungarian method or algorithm might give you the wrong solution. So if the total number of rows and the columns in the given cost matrix are unequal, then you have to add the what it calls the dummy rows or the columns before it is solved by the Hungarian algorithm. Okay. So and then once the cost matrix is balanced or standardized, then you can start the implementing the row reduction and column reduction and just follow these steps. Okay. Okay, so actually I will modify this original example just a little bit. Just change the numbers here and there just a little bit. So let's find the least cost assignment for this cost matrix using the Hungarian algorithm. So the first step, or call it step number 0, you standardize the given cost matrix. So it's obviously they have same number of rows and same number of columns. So you don't need to do the step number 0, right? It's already been standardized cost matrix. So it's safe to move to the next step, which is row reduction. So in this case, 4 is subtracted, right? 4 is subtracted from each cost in the first, second, and the third row. And the 3 is subtracted from the last row, right? So the resulting table, cost table, is like this. Now we conduct the column reduction. So in this case, just like the previous example, only column number 3 doesn't have a 0 value, right? So the column number 3 is reduced. So 1 minus 1 becomes 0, 1 minus 1 becomes 0, 2 minus 1 becomes 1, 1 minus 1 becomes 0, right? All the other columns remains the same. 4. Now we need to conduct step number 3. So in step number 3, we need to find the minimum number of lines that are required to cover all of the 0 values in the cost matrix. So the here the keyword is the minimum. Okay, we need to find the minimum number of zeros. Minimum number of lines that can cover every zeros. So of course, by drawing 4 different lines, you can cover every zeros. But the thing is, you have to find the minimum number of lines that can cover 0. So in this case, by using only 3 lines, you should be able to cover every zeros in this cost matrix. So in this case, the minimum number of lines required to cover 0 will be 3, right? So I'm gonna write it down. Here, the minimum number of lines that can cover every zeros would be 3. Right? One line here, 2, right? And what is the total number of rows or the columns? The same. In our case, we have 4 different rows or 4 different columns. And this number is not equal to the minimum number of lines, right? That is required to cover every 0. So in this case, we need to move to the next step. Okay. If this minimum number of lines required to cover every 0 is 4, which is exactly the same as the total number of rows for the column, then we're going to stop here because this will indicate that we should be able to find the minimum. We should be able to find the 0 cost assignment. But this is not the case, right? So these two numbers are not the same. We need to move to the next step, which is step number 4. Okay. So I'm going to tell you that the step number 4 here involves creating the additional 0 elements without creating any negative elements. Okay. So notice that the smallest online cost is 1 here. So the smallest the online cost is 1 down here, right? Among these 6 different numbers, 2, 3, 2, 4, 2, 1. maybe you missed what I discussed about the Hungarian algorithm. We are in the middle of the algorithm, so
I'll go
please,
back.
yeah, look at it. Okay, so here the smallest online cost is 1. So we're gonna subtract the same amount 1 from every element in the entire table. So let me use the Excel spreadsheet. So let me copy this 4 by 4 matrix first. 2, 0, 0, 1, 3, 0, 0, 3, 1, 0, 2, 0, 0. Okay, so here is 2 lines. So we identify the minimum online cost is 1. So we're going to subtract this amount from every location. It's going to be 1, 0, 0, 1, actually -1, -1, 0, right? 2, -1, -1, 1, -1, 2, 0, -1, 1, -1, -1, 3, right? Okay. And then next, what you're going to do is in order to, okay, so after you subtract 1 from every location, what you notice is we created a new 0 element in this new position, right? So that's the point why we subtract the minimum online cost from every location. But next is in order to restore the previous 0 element, it's here, right? And also eliminate negative elements. So we have negative elements up here, right? What you need to do is we're going to add the same amount of 1 to each row or the column with a line covering it. So we're going to add the same amount of 1 to this column, this 2 column, and to this row. Okay. So first, let's add 1 to this column. So in this case, we have 0, 0, 3, 0, right? And let's add the same amount 1 to this column. So we have 0, 0, 1, 0. Now we're going to add the same amount to this row. Okay, so we have 0, 4, 2, 0. Okay, so I believe this matrix is exactly same as this one. Okay, and there is alternative way to obtain this same matrix. So down here, just say alternatively locate the smallest aligned cost and subtract this cost from all aligned cost and add to the cost at the intersection of line. So let's do this time. So I'm going to copy this. What you need to do is here again, you're going to identify the minimum, the smallest aligned cost again. So among these 6 different values, the smallest aligned cost is 1, right? So we're going to subtract this amount from these 6 different locations. So we are going to have 1 instead of 2. We're going to have 2 instead of 3. We're going to have 1 instead of 2, right? And then we're going to have 0 instead of 1. 1 instead of 2. 3 down instead of 4. Okay. And next, what you need to do is just add the same amount at the intersection of the lines. So the intersection of these 3 lines, these 2 locations, right? We are going to add 1 to this location. So we're going to have 4 and 2. And all others remains the same. So I'm going to simply copy this. Okay. So let's compare these 2 matrices. These 2 matrices are identical. Okay. So there are 2 different ways to conduct step number 4. Okay. So just keep in mind that the step number 4 has the purpose of creating the additional 0 element on this cost matrix, okay, which is right here. We have additional 0 without creating any negative elements. Okay, that's the purpose of conducting this step number 4. Okay, so we have this new cost matrix, right? This is our new cost matrix, which is exactly same as this. Okay, just copy from the previous screen. Okay. So okay, so this new cost matrix has a 0 value, right? Which is up there. That is not covered by a line. So now we do need another line, right? In addition to these 3 lines. Or you can start over using with this new cost matrix, trying to find the minimum number of lines that are required to cover every zeros. So obviously, you do need 4 different lines, right? There is no way to cover every 0 with only 3 lines, right? Definitely, you do need 4 lines to cover every 0. So in this case, the minimum number of lines it requires to cover every zero. It's going to be 4, right? And the total number of rows or the columns, this cost matrix is 4. These two numbers are equals, right? So you have to stop here. Because this fact indicates that you should be able to find the zero cost assignment from here. Okay? So how you can do this? I can use this table for the zero cost assignment. So in order to do the zero cost assignment, what you need is to first identify any rows or column that has only 1 zero value. Okay, so let's consider this matrix. Let's consider this matrix. So here, definitely the first column has only 1 zero, right? Okay, so because the first column has only 1 zero, you have to choose this location for the zero cost assignment. So I'm gonna mark it as red, okay, and then I'm gonna mark it black. To prevent any further assignment in the future on this column and row. Okay. Now, this column, last column, has only 1 zero, right? So I'm going to choose this. And then, likewise, I'm going to make black the same row and same column. Prevent from further assignment. Okay. Now we seems have two different zero cost assignment available in this case. So if you choose this, then you're gonna choose this, right? But if you choose this, then you're gonna go with this. So actually you have two different solutions. Those are this. Okay. And of course, both of them are optimal for this problem. So what you need is bring back the original cost matrix. So in this case, the optimal assignment cost corresponds to this location and this location, for example. So we're gonna get number 4 and number 5, and then 5 plus 3. So it's gonna be 22 22 would be the optimal assignment cost, right? 4 plus 3 plus 5 plus 5, or 5 plus 4 plus 4 plus 4, plus also 22, right? So we do have multiple optimal solutions in this case. Okay, so let's take one of the class textbook example problem. So I got this from our textbook, chapter 8, the end of chapter problems 3-2. It's going to be either from, I believe, 10th edition or 11th edition. Okay, so let's read the problem description together. So in this example, 4 different cargo ships will be used for shipping goods from one port to 4 other ports. They are labeled number 1 through number 4. And any ship can be used for making any one of these 4 trips. But because of differences in the ships and cargoes, for example, the total cost of the loading, transporting, and uploading the goods for the different ship port combinations varies considerably. Okay? And they are shown in this table. So the goal is to assign the 4 ships to 4 different ports in such a way as to minimize the total cost for all 4 different shipments. So as the first step, please describe how this problem fits into the general format for the assignment problem. And then obtain an optimal solution. Please use the Hungarian algorithm that we just talked about for finding the optimal solution. So how do you answer for the question number A, first question? How this problem can be fit into the general format. Yeah, so yeah, that's basically it. So definitely in this case, if you think the ships are the assignees, right, and the ports are the assignments, then this problem will fit into the general format of the assignment. So let's do that. I'm going to use again Excel spreadsheet. Put these numbers down. Okay, so let's do this. So let's conduct the first first of all, you need to check if this given cost matrix is already standardized. So obviously it's yes, right? The total number of rows are equal to the total number of columns, right? So yes, it is. So we're going to move into the next step. So we're going to basically follow this task. Okay. So we just done the first step. Now we need to do the row reduction. So we're going to find the smallest cost from each row and then subtract it from each row. So the first row, the minimum number is 400, right? And second row is 500. Third row is 500. And the bottom row, the minimum numbers is 400. So we're going to subtract this amount from each row. Okay? So for the simple computation, I'm going to copy this number. Make 4 by 4 matrix. And then here, I have this minus this. Then, so after the row reduction, we end up with this matrix. Okay. So I'm going to copy this matrix down here. Just need to copy it. Just copy the values from here. So this is exactly the same as this. Now we are going to conduct the column reduction. Okay. Again, we are going to identify the smallest cost from each column and then subtract it from each column. So the first column, the smallest amount is 100. I'm going to write down 100. Second column and the fourth column, the smallest amount is 0, right? Nothing's going to be changed in those two columns. So I'm going to still mark it, record it, the minimum cost of those two columns. And the third column, the minimum amount is 200. So I'm going to copy. Okay. So after the column reduction, we end up with this matrix. Okay. Are you following me? Okay. So now, what's the next step? Next step is we're gonna need to find my cursor. We need to find the minimum number of lines. Okay. That can cover every 0 element in the cost matrix, the reduced cost matrix. So here the keyword is the minimum. Okay, we're gonna identify the minimum number of lines that can cover every 0. Here, so how many lines are required? Does 3 lines can cover every 0 here? No way. We need 4, right? So we need 4 lines to cover every 0. But this is not a good example because I want to go through the step number 4, but it looks like we don't need to go there. So here, the total number of lines, the minimum number of lines required to cover every 0 is 4, right? This is the number of lines are covered every 0. Right? So in this case, we do need require 4 different lines to cover every 0 element. And this number 4 is exactly same as total number of rows for the columns, right? So this is exactly same as total number of rows. So we're gonna stop right here because this fact implies that we should be able to find the 0 cost assignment based on this table. Okay. So again, in order to do that, we need to identify any rows or columns that has only 1 0. Okay. So in this case, the last column has only 1 0, right? So you must choose 0 here. I'm gonna mark it red. And then mark the other values in the same rows and same columns to prevent further assignment in the same row. Okay. Now, do we have any rows or column that has a single 0 value? No, right? So this indicates that we do have multiple solutions, multiple optimal solutions. So you can go with this 0 or 0 down here, or any 0 values. Okay, in this case. So I'm going to choose this 0. Okay. And then mark it as black. Again, we have 2 different options available, right? So if you go with this, for example, and you're going to mark it, you can choose this. Okay. And then go back to the original cost matrix. This is this. Okay, so this is the original cost matrix, right? And then we're gonna choose the same location. Here, 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 here. Because in this case, you do need to add up all these 4 numbers, right? To get the optimal assignment cost. So in this case, 2100 would be your optimal assignment cost. And then what is your decision? Your decision is shift number 1 has to be assigned to port number 1, and shift number 2 has to be assigned to port number 4. Shift number 3 has to go to port number 2, and shift number 4 has to go to the port number 3.
How did you get that?
Because
the
correspond to this
I see.
optimal sign. Okay. And of course, you also need to report that the corresponding optimal assignment cost would be 2100. That's what I mean. Okay. So let's consider another example. I believe this is the last example for today. So again, you can use Excel spreadsheet for doing that. So let me give you a couple minutes. Why don't you try to do that? Okay.
What happens if it's not standardized?
This is not standardized. Okay, that's a good question. So in this case, we have 4 different strokes, but we have 5 different swimmers, right? So in this case, because it's not standardized, what you need is to add one more row. Right? Add the bottom row, one more row with 0 cost. Okay, that's what you need to do. In this case, I'd say there is a dummy style. Okay. There's a dummy stroke, and then what you need is put 0 values. Now you have 5 different strokes and 5 different swimmers, right? So now you should be able to implement Hungarian algorithm. That's a good question. Okay, so let's do this together. I got the first matrix here. So let's consider the time matrix as the cost. So we're gonna do the row reduction to identify the minimum value from each row. So use the Excel function. Minimum value of this. Done. So I'm gonna just copy. So that the minimum number. Okay,
Do we do it 4 or 5?
which one?
Do we copy it? Do you copy?
Oh,
it?
yeah, fine. Yeah. Yeah. So I'm gonna subtract these numbers from here. And this. Now I'm gonna copy this down here. Now we need to conduct the column reduction, right? So we're going to identify the minimum number from each column and subtract it. Just going to put the minimum number. This. No. Sorry. I forgot one thing. One very important. I forgot to add 0 values. Right? Okay, so actually the column reduction is not necessary because as you can see here, every column has at least 1 0, right? So the minimum number from each column is not 0. So nothing's going to be changed after the column reduction. So now we should be able to move to the next step, which is identifying again the minimum number of lines that can cover every 0 values. So here, obviously, you can draw 1, 2, 3, 4, and 5 different lines, but the thing is, we're going to find the minimum number of lines, right? So that's going to be 2 different lines. So enough to cover every 0, right? So we need 2 lines, but how many different rows we have? We have 5 different rows, right? Those 2 numbers are not the same. So we need to move to the next step. Which is step number 4. Okay, just like we did earlier here. It's up to you. You can go the first way or the second. But let me go with the second one. So what you're going to do is locate the smallest unaligned cost and subtract from every unaligned cost and then add to the intersection of the lines. Okay, that's what you're going to do. So here, what is the minimum unaligned cost? It's like 0.9, right? Among these 16 different locations. 0.9 is the minimum. Okay, so we are going to subtract 0.9 from every aligned area. Okay, so here we have 4.8 minus 0.9. The same. Zero, right? And then we're going to add the same amount, 0.9, the intersection of this line, 2 lines. This is one here. So instead of 0, we are going to have 0.9. And all other locations, we're going to have the same value. Those are zeros. Right? 0, Okay. Okay. And what's the next step? We go back to the first step. Again, we need to do the rule reduction. Okay. So basically, you're gonna repeat this step over and over until you find the 0 plus assignment. So let's do the rule reduction. So here, we're going to just copy. This number. So we're going to identify the minimum value. Still, okay. Okay, because we have 0 every row and every column. So row reduction and column reductions are not required, right? So again, what you need is identify the minimum number of lines that can cover every zeros. So this time we need 1 line and 2 lines, but we need 1 more line, right? So let's draw this one. So we do need 3 lines, but the number 3 is not the same as the total number of rows, which is 5, right? So again, we need to identify the minimum aligned cost and subtract it from the aligned area and add the same amount to the intersection of the lines. So 0.7 is the minimum value, right? Okay, so we're gonna subtract that amount from here, minus 0.7, and do the same. Equation here and here. Yeah. And then we're gonna add 0.7 to this location and this location, right? And then copy all the other numbers because they are the same. This is same as this. And same here. Yeah. Okay. Okay. Now, again, the row reduction and column reductions are not necessary because we have 0 values every rows and every column. So again, we need to identify the minimum number of lines that can cover every 0 values. So how many lines do we need? Obviously, we need 1, and then 2. And 3, 4, right? So this time we can cover this way. So here, okay, but obviously we do need 4 different lines. And this number 4 is not the same as the total number of rows or column, which is 5. So again, you need to identify the minimum aligned cost and subtract it and also add it. So the minimum aligned cost would be 1.2, looks like, right? So we're going to subtract this value. 1.2 minus 1.2. So we create new 0 here. And then we're going to add 1.2 to the intersection of the lines, right? So here, 0.7 plus 1.2. And here we have the same number,
So are you always adding it on the intersection of the
right?
rows? So why is, the last matrix a 0.7 on the intersection? Instead of 0.7 plus.
Is that this one?
And then the next one,
Oh, really?
so should that be added?
Yeah, we have to add it 0.7 and 0.7. Thank you. So here, okay, this, let's do this value plus 0.7. This. Thank you. Anything else? Thank you for finding the error. Okay. So how we're going to copy from the previous. Okay. Now we need to find the minimum number of lines. Cover every zero values. Yeah. So you need to find, right? One, two. There is no way to cover these three different zero values with two more lines. Is there any way we can do? So 1, 2, 3. So we still need to cover two more zeros. So obviously we need 5 lines. So in this case, we do need 5 different lines, right? Obviously, that's gonna be the minimum number of lines required to cover every zero values, which is exactly the same as the total number of rows or columns. So now we're gonna stop right here because this implies that you should be able to make a zero cost assignment based on this reduced cost index. Okay. So let's do that. Again, we need to identify the any rows or columns that has only one single zero value. So that's going to be either the top row or the last column, right? So I'm going to go with this first. I'm going to choose this, and then the color. Now we have this column and this column, and even this column, and this row. We have 4 different candidates, right? So we have ties, and just arbitrarily choose either. Let me go with this top row. Market. Now you have, choose this. And now you must choose this, right? You cannot choose this. This is the only 1 0. This column, right? So I believe this is the original matrix, right? So referring to the original matrix, we need to identify same location that is yeah. So here, if I bring back to our problem, yeah. So what is your optimal solution?
126.2.
Okay. So let's do the optimal assignment first. So here, backstroke. The backstroke was going to be assigned later, right? And last stroke, we're going to assign 20. And butterfly, we're going to go with Chris. Freestyle, we go with Paul. And Ken will be the first standby. Okay. And the optimal best times. How much is that?
126.
126. Is plus 126. That's our this is our solution. Okay, so any questions? So I just say the Hungarian algorithm, the implementing the Hungarian algorithm is very easy, right? But still you do need a practice, okay? Otherwise you will get confused. There are a couple of things you need to keep in mind for every step of the Hungarian algorithm. So definitely, I would recommend you to do the practice. Okay, so any questions? Okay, if you don't have any questions, then I will see you guys this coming Thursday. Thank you very much.
Thank you so much.